So what is an acid? By definition, an acid is any chemical that dissociates or comes apart in water to increase the hydrogen ion concentration. It's acting as an acid. It's increasing the hydrogen ion concentration. A base, on the other hand, is anything that combines with hydrogen to take it out of solution. It will absorb or combine. Absorb's not really an accurate word technically, but maybe you can visualize it's taking up, combining with those hydrogens. Or it might be creating hydroxides. That's another way a base can work. If it's creating hydroxide ions, what do hydroxide ions do? A hydroxide ion bumps into a hydrogen and makes water. So indirectly, the base that creates hydrogen, or excuse me, a base that produces hydroxide ions, OHs, will combine with the hydrogen ions, but in this case, forming water. So why is pH important? Well, we have a mixture of soil components, minerals, nutrients, and toxins like aluminum, or even nutrients that can become toxic like molybdenum, and organic matter, both the living and the decomposing organic matter. That all is in the soil. And the pH of that soil will have a huge impact on the availability of the nutrients that are in the soil. And I'll show you that in just a minute. It also has an impact on the living things in the soil. It has an impact on the availability of or concentration of toxins that might be in the area. And it's not just in the soil. If I change the pH of my blood, it could be lethal. We have a very narrow range that's survivable for human blood. We need our pH of our blood to be stable. So here, just to give you an idea of what this is representing, across the top we have the pH scale, or a portion of the pH scale, from 4.5 to 8. And why is it only 4.5 to 8? Because this represents realistic soils that you might find in productive environments, growing plants, or agricultural environments used to grow plants. So you can find some soils, or you can grow crops a little above pH 8 in some situations, but it's rare to find that out in a natural environment. So that's the pH going left to right. And all of these colored bands are labeled with a subset of the 14 nutrient elements. There are 17 essential elements that all plants need. 14 of them are considered nutrients. And we have a large group of the 14 nutrient elements, plus aluminum, which is a toxin, that are shown on this chart. And the wider the band, the colored band for any given nutrient or toxin, the more available it is to plants. So for example, with nitrate, between 6 and 7.5, nitrate is easily available to plants. But you start getting above 7.5 and it rapidly goes down. Below 6, it also starts thinning. Something like calcium is, if there might be tons of calcium in the soil, but in acidic soils, calcium is not very available to the plants. As soon as you get above a neutral soil, especially above 7.5, kaboom, calcium becomes extremely available to plants. And it's just the opposite for iron. So if I change my pH to be favorable for calcium and I go too far, my plants can't get iron. It's a balancing act. And if I'm too acidic, I go down there below 5.5, I'm at a risk of having aluminum toxicity. Aluminum is never a plant nutrient. Or, I'm sorry, I said molybdenum with the acidic, I think, but molybdenum can be a problem in alkaline soils. It's the manganese that is toxic in acidic soils. This is toxic. So again, the pH in the soil has a huge impact on the availability of the nutrients or the potential toxicity of substances in that soil, among other things. You don't have to memorize this chart. If I were you and focusing on studying, I would focus on the language that in acid soils, calcium, phosphorus, and magnesium become chemically unavailable. Calcium, phosphorus, here's the phosphate in brown, it kind of thins down over here, and magnesium become chemically unavailable, while manganese and aluminum can become toxic. In alkaline soils, micronutrients such as iron and zinc down here and copper can become chemically unavailable. All right. What about pH in wines? pH is important to determine the ripeness and make harvest estimates. pH is important during fermentation, and it's important for the final character, the mouthfeel and taste and other characteristics of the wine. The lower pH, the more acid a wine is, the more tart or sour it will taste, and we also call that crispness. The tartness gives a crisp feel in the mouth. Higher wine pHs are more susceptible to bacterial growth and spoilage during fermentation, so that can be a problem. Most wine pHs fall around 3 or 4, and with the whites being slightly more acidic on average, closer to 3, with the reds being maybe a little bit more. The exact range depends on who you ask, but they're all close to this general range. What about buffers? A buffer is a chemical that resists change to pH. pH only tells us what is the hydrogen ion activity in a solution at this moment. In my soil, in my grape juice, in my wine, what is the hydrogen ion activity at this moment? But as I add other substances that might have their own pH characteristics, there's something called buffers, which will resist changes to pH. And so we look at the buffers as chemical hydrogen ion reservoirs. And a buffer is a chemical that will combine with hydrogens, removing them from soil when we add hydrogens or add acids. And buffers will release more hydrogen ions if we add a base. It will counteract or resist the change to pH. That's a buffer. And buffers are naturally occurring. They're not just biological. They're not just in living things. There are many compounds that come in the formation of soil directly from the rocks. The inorganic chemistry of the surface of the earth creates some buffers. Carbon dioxide gas itself becomes a buffering material in a water solution. Hydrogen ion reservoirs that take up or release hydrogen as needed. We call these a weak acid-base pairs because if we look at some acids like hydrochloric acid in our stomach, hydrochloric acid is hydrogen plus chloride or chlorine. And when they come apart in water, you have hydrogen atoms and chloride atoms. And they all come apart in water. So it's a strong acid. There's no buffering capacity. If I put hydrochloric acid salt in water, it all comes apart, unless I put way too much. But some things do not come all apart. They come apart to act as an acid a little bit, or they can act as a base. And I'll show you that in this chemical reaction. Here is a water molecule. And let's imagine this is a raindrop in a cloud. And in that raindrop that is forming in a cloud, we have some gas dissolving in that raindrop, some oxygen and other things. But here comes along a carbon dioxide molecule dissolved in that raindrop. And the two can react with each other, forming carbonic acid. That carbonic acid can then come apart to form bicarbonate and hydrogen ions. Why do we call it carbonic acid? It's an acid because it is a chemical that can come apart, increasing the hydrogen ion concentration. And what do we have here? A hydrogen ion. And in that same drop of water in the cloud, this is going on millions of times. And I'm getting hydrogen ions. Therefore, the pH of a raindrop is not 7, neutral. It is slightly acidic. And there's other things going on in the water. This is just one thing that's going on that it partially explains what's going on. But bicarbonate is a base. Why is bicarbonate a base? Because it does have the ability, when it bumps into a hydrogen ion, to go back into carbonic acid, taking that hydrogen ion back out of solution and turning it back into carbonic acid. And it's got a double-headed arrow between the two because some of it's going to be bicarbonate, some of it's going to be carbonic acid, back and forth. And which direction the reaction goes depends on the environmental conditions at that moment. But on average, at any given moment, all 3 of these white rectangles, all 5 of these compounds are in that water droplet. There's water, dissolved carbon dioxide, carbonic acid, bicarbonate, and hydrogen ions, which means it's slightly acid. There's no hydroxide, OH, ions in this, and that's not likely with the things that are likely to be in a raindrop or in a river, freshwater, clean river. Anyway, so what happens if hydrogen ion concentration is low? How could I make hydrogen ion concentration low? I could add a tiny bit of base to my raindrop, taking away or combining with these hydrogen ions. So if I take away some of these hydrogen ions, what's going to happen? More of the carbonic acid is going to turn into bicarbonate and hydrogen ions. Essentially, if I take away some hydrogen ions, the carbonic acid that's left is going to replace them, or at least some of them. Not all of them, but some of them will be replaced. And if I do the opposite, if I add a little more of the hydrogen ions, then the excess of hydrogen ions is going to have a high hydrogen ion concentration. It will combine with the bicarbonate, turning back into carbonic acid. So again, I take away hydrogens, the carbonic acid releases more. I add hydrogens, the bicarbonate's going to turn back into carbonic acid. I can resist changes to pH because of buffers. Now, carbonic acid and bicarbonate is a weak, minor buffer. There's lots of other buffers in the soil and in your plant tissues and in my tissues and in the natural environment all over the place. And these buffers stabilize the pH at a certain point. And every buffer has its particular point where it stabilizes the pH. And the combination of buffers in my blood stabilize the pH around pH 7. In other solutions, in other environments, the pH might be stabilized at a different level. So musts and wines are titrated to determine their pH and buffering capacity. Here you can see a simple setup with sodium hydroxide base, a pH meter, so I'm measuring the pH of the wine, and then I'm adding the sodium hydroxide until the pH reaches some set point. And that tells me how well the wine was able to resist the change in pH. The more sodium hydroxide it takes to raise the pH, the stronger the buffering is, or the titratable acidity is in my wine, my TA number. The more sodium hydroxide it takes to run the experiment to increase the pH, the higher the TA, titratable acidity, is in my wine. And I can do this either with a manual setup like in this illustration, or here is a very modest machine, one of the lesser expensive setups, a small one that you can buy to automate the process in a winemaker's lab. So we call the measure of buffering capacity in a wine, we call that the titratable acidity number, or TA, all right? And that is it for pH and buffers.